This is the classic clock reaction, and we're going to grab sodium thiosulfate and hydrochloric acid, and we're going to use different concentrations, and it's going to create sulfur, which is a precipitate, and the sulfur dioxide will come off and be smelly. Sodium chloride you won't see, and that will get cloudier and cloudier, so you can't see the X's anymore. So the first thing we do is we're doing 5 concentrations. So that it all adds up to 50 mils, and so we're just doing 50 mils, 10 mils of water, 40 mils of sodium thiosulfate, 10, and then 20, 30, 30, 20, and then 40, 10. All right, so they're all mixed together, and so those concentrations are here: 0.15, 0.12, 0.09, 0.06, 0.03. And this is how you do the calculations for the second beaker. So that's 0.15 sodium thiosulfate, 40 mils of that. That gives you that many moles. Added 10 mils of water, so that's the concentration for the second beaker. Okay, and now we've measured out 5 mils. I'll just give it a quick shake and quickly add 5 mils of 2 molar HCl to all of them. And the reaction now starts. Okay, and then we just time it. Now I've just taken times off the video to see how long it takes. And so I started about 1:15 on the video. It stops at about 1:38. And so that's 75 seconds to whatever seconds the difference is here. And so that's how long each of these ones took. And so you can see it just gets cloudier and cloudier, and then all of a sudden you can't see the X. And as soon as you can't see the X, that's stop. All right, that's called the clock reaction. It stops at a certain point. Okay, so you get all those numbers and divide them by seconds, and you can get a rate. That's not the proper way to do a rate. The proper way to do a rate is you must do the moles per time. So that's sort of the cheat way to do a rate. It's not the proper way, so you can't do a full rate equation. You can't work out what K is. And when you graph it, you get a nice straight line. So that's concentration, rate versus concentration. And so it's come to an end now. And so the rate versus concentration graphs are here. So it's first order, it's a straight line. So that tells you it's this reaction here. So that's a first order. And so the effect of concentration is first order, which means you double the concentration, you double the rate. Okay, if it was zero order, it would have no effect on the rate, that particular species. If it was second order, it would have an exponential effect. Main issue with this experiment, you can see from the picture here that the final concentrations are quite difficult. And it's almost to the point where that concentration is not even strong enough to hide the X, and that would go infinitely. And that's what you might expect if you had this going on here. If you didn't have a strong enough concentration, down here it might be fine, but up here you may never get a reading for the last 3. It may never ever have had enough precipitate. It just so happens, as you'll see in part 2, it shows you how to do the experiment properly. So make sure you watch part 2 of this. We use a spectrophotometer, and it reveals that it's actually increasing at an increasing rate, which is quite unusual. So in most cases, unless you go right up here, in most cases you're going to be safe. Even though it's a low concentration, it will be fast enough and enough of it to cover up the X. Now, the main reason this is a bad reaction is because of that. You don't really know what's going on because you didn't take continual values, which spectrophotometers do, and you're not taking initial rates. So the rates are usually, as you can see from here, the average rates, say if we did it from here, are usually slower than the real rate. But in this particular one, the average rates are actually, the initial rate's actually faster than the average rate. So you always do initial rate. So to do it properly, you should do moles, a decrease in moles per second. Now we just did the quick and easy way to do it. And you should also do initial rates because the temperatures are changing and also the concentration of reactants are changing. And for this one, the catalyst is actually increasing as well. So the only time you get an accurate rate of reaction is initial. You have to draw a tangent to the line. Watch the videos on how to do initial rate. average rates don't control your variables. So you should, now that you're in year 11 and 12, never do an average rate. Always do initial rates. And do take it that one step further to write the rate equation, because it's not that much more, but then it gives you the actual answer of it so you can understand what's going on. Okay? Okay, so that's how you do it. Make sure you watch part 2 to see it in more detail.